I'm obsessed by the Habitable Worlds Observatory right now, and I don't think I'm alone. I suspect you are as well. And this is, of course, a next-generation space telescope that is under development at NASA that hopefully will give us the first direct images of Earth-sized worlds orbiting around sun-like stars. It will allow us to measure the atmospheres of those worlds and hopefully find biosignatures, the very life signs that there is something alive on these planets. Now, this is a very tricky problem, and that there are certain wavelengths that need to be detected by the telescope to be able to give you information about these biosignatures. And the further into the infrared that the telescope needs to go, then the more complex and engineering challenge it's going to be for Habitable Worlds Observatory. The ideal is that you have ones that are detectable, they're easily, you don't have to cool down the telescope. It makes the engineering simpler. And so my guest today has done the math. My guest is Celeste Hagee. She is a PhD student at the University of California at Riverside. She has analyzed the kinds of signals that you might be expecting to come from these Earth-sized worlds orbiting around sun-like stars, the ones where you're looking for this interplay between methane and carbon dioxide and water in this atmosphere. And the question is, will HWO in its current configuration with the coronagraph that it's going to be equipped with be able to detect those biosignatures? You'll find out the answer in this interview with Celeste Hagee. Celeste, let's fast forward maybe 20 years. The Habitable Worlds Observatory has launched. The data are coming back home. You're looking through them to see what you can find. What would you be hoping to see? What would be exciting?
Yeah, well, with the Habitable Worlds Observatory, of course, we're going to be trying to detect and characterize these Earth-like exoplanets around some like stars, and so we really want to see these biosignatures, right? So we could be looking for water, methane, oxygen, ozone, and even carbon dioxide as well. And I know that they are currently working on these novel biosignatures such as methyl halides, so CH3Cl, CH3Br, CH3I. So using this, direct imaging and reflected light spectroscopy to detect these molecules would be super important to understand the, context in which these planets have developed, and really comparing Earth, using Earth as an analog to study these planets will be really great to see how they develop over time, how these molecules and their abundances change over time, and what that means for life, and if we can detect life. And it will be just really exciting to even have this opportunity to do so.
I mean, we're at this point now with Webb that we can detect the presence of many of those molecules that you just mentioned. They're just in the atmospheres of planets that are terrible.
Yes.
Gas giants, hot Jupiters, things where it's raining metal, places you probably wouldn't want to live. And then other things that are a little more ambiguous, and yet we're still sort of in this era that we've failed to detect an atmosphere around any planet orbiting around a red dwarf. And so I guess that perspective would be, okay, you're seeing a lot of those same chemicals that have been detected so far, but now we're seeing them on a planet that is Earth-sized, orbiting around a sun-like star within the habitable zone.
Yeah. And, what's really unique about the Habitable Worlds Observatory is this is kind of the first flagship mission where that's a unique goal of ours. It's really, of course, it will do a bunch of different astrophysics, science. But this will be the first mission with the unique goal to detect life, characterize life on different planets. And, we're able to do so because we're developing these really awesome technologies, like the Coronagraph, for example. So I know right now Roman has a great Coronagraph, and I believe that it will be able to kind of look at Jupiter-sized planets. And so what's the Habitable Worlds Observatory, it will need to kind of increase that contrast ratio to 10 to the negative 10, which will enable us to look at these Earth-sized planets.
What does that compare? I know it's the brightness difference is 100 million to 1 for Roman. What is 10 to the 10? 10 billion?
Yeah,
Sorry?
I think it's 10 billion, yeah.
Ugh.
So, just even
1,000.
Yeah, so even that much will give us that information that we need to really look at these smaller planets, which is just so great to think about, like, that we'll, hopefully be able to do that in, the 2040s.
It is strange though. Like right now, we still don't even know of a single one. Like we haven't, like it's not even we haven't even characterized their atmospheres. We don't even know if we don't know of any yet.
Mhm. Yeah. Well, there's that bias for, observational bias where we're seeing like larger planets because, of course, they block more light when they pass through a star, like through transits, for example. And then also, shorter periods as well. That's another bias because we'll see them more. So it's a more likely chance that we're going to see them. So yeah, like having a mission that will be able to search for these tiny planets, like, 10, 25 parsecs away, like that will, really open up our eyes to, what is the chance for life to be out there? And of course, if we don't find life, how does that translate into like how special Earth is, right? And how we can, do our best to, conserve Earth and like protect Earth and all of that, right?
So your work, the paper that sort of brought you to my attention, was that you were looking at the constraints of how good, I guess, the coronagraph will need to be able to deliver the kinds of observations that the astronomers need to make. So give us a sense of what you did to sort of consider this problem.
Yeah, so with the Habitable Worlds Observatory, we're looking at this long wavelength cutoff in the near infrared. And so there has been a lot of discussion on how far do we need to go to be able to detect all of these molecules of interest that could, you know, lead us to think that life could be on these planets, while also not making the engineering and the cost too complicated and costly. And so once actually a paper written by Lee talks about like as you go past 1.7 microns, you have to start cooling the telescope, which results in a whole bunch of, engineering complications. And, you have to cool the whole coronagraph system. And like there is, some mirror stability issues and like everything like that.
Yeah,
And
we actually
so,
talked about that in our interview.
yeah,
That exact details, right? Yeah.
yeah.
So sorry, I just want to clarify this, right?
Yeah.
That we look at James Webb. Really, the engineering challenge with James Webb was about keeping that telescope cool enough so that it could observe in those wavelengths. Like that is Lee was saying the very shape of the sunshade is designed to really scatter that heat to make sure that temperature stays cold so that you can observe those wavelengths. But because HWO is going to be more of a visible light telescope, it doesn't need to be cooled down. And so now the emphasis is put on the coronagraph as opposed to necessarily that keeping the telescope cold.
Yeah. So yeah, really our goal is to see, can we do all the science that we want to do without having to cool it, and doing and having to face all those challenges that James Webb faced and everything. And so my work, I use a methodology called Bayesian analysis for remote biosignature identification on exoEarths, which is also known as BARBIE.
Okay, good. There had to be
yeah.
an anagram there. Yeah, okay.
Yeah. So if you, read the paper, everything's like pink and, very on theme. My mentor at NASA Goddard Space Flight Center, Dr. Natasha Latouf, created this methodology for her dissertation. She's now an MPP at NASA Goddard. Still, working on BARBIE and everything. But what BARBIE basically allows you to do is see how the detectability of a molecule varies with respect to signal to noise ratio, wavelength, and molecular abundance. So you're really able to see, like, depending on, A, B, C, D, how can we get this strong detection of a molecule? And so particularly, I was looking at carbon dioxide and how carbon dioxide interacts with both water and methane, because if you look at a spectrum, you're going to have a lot of different overlapping spectral features, and that's one of the challenges, right? We have to disentangle these spectral features, figure out what's coming from what, figure out like what's the abundances of each. And so BARBIE is basically you use retrievals, which are statistics to analyze the spectra, and that will kind of give you information about different atmospheric properties. So like the molecular abundances of molecules, the the surface albedo, surface pressure, gravity, etc. And so you're really able to figure out what's kind of happening in an exoplanet atmosphere. And what's really cool, so BARBIE uses grid-based retrievals. So basically you kind of preset these spectra. So there are 4 different ones. There is Merman, Beach, Lifeguard, and Allen. So, again, very on theme. But each of these grids tackle a certain set of molecules. So you have to pick a molecule that you want to study within these grids. But the benefit of this, like compared to a, normal like MCMC retrieval, is that it takes a lot less time when you're actually running it. So it may require some, upfront computational time to actually build the grids, but once you're doing it, it runs a lot faster, like on the order of, seconds, minutes, instead of like hours, weeks. And so that was really great to run those.
And I'm going to need to get a little more information from you because there's like, we're fine here on this channel with fairly technical language, but I just want to sort of understand here.
Yeah.
So is the issue that certain molecules, say carbon dioxide, have very similar spectral lines to other molecules, and getting a really strong signal for one chemical is the challenge? Is that, I'm trying to understand why you have to sort of have this grid system. Why don't you just focus on one molecule that you're trying to find and then just find out what it takes to bring that signal up?
Yeah, so the main thing is that, when you're looking at a spectrum, this is it's all of the molecules all together, right? And so the goal is to disentangle them, really distinguish what's coming from what, and that can be a really hard thing to do, and that's kind of what the retrievals are getting at. They're kind of predicting what molecules are at what abundance, so that it's kind of matching the spectra that you're seeing.
Okay. So sorry. Let me just make sure. I want to make really sure that I understand this. So essentially that there are, I guess, Bayesian predictions that have been made where you throw thousands and thousands of different atmospheres, millions maybe, at this computer. It trains and understands that this composition of these different chemicals in this atmosphere gives you this kind of signal. And so that when you then analyze the potential signal from an atmosphere, what are the constituent chemicals that are making up that atmosphere, because your spectral lines aren't going to be like strong enough to go, there's carbon dioxide, right? Instead, you're like, here's a weird combined spectrum for this atmosphere, so it probably contains all this. Am I understanding this correctly?
Yeah. So, really what you're seeing depends on a bunch of things, right? It depends on, signal to noise is one thing, how much of a molecule is in the atmosphere in the first place. And so that will really tie into what kind of atmosphere you're seeing, what spectral features you're seeing. But yeah, it's really trying to get, this, you kind of working backwards in a way where it's like you're seeing this spectra, and then based on known, physical properties of the chemicals and the molecules, you're trying to predict what certain combination of all these molecules and their abundances will make that spectra.
Got it. Okay. All right.
Yeah.
All right. So it's like, I'm just an analogy. You're looking at pictures of soup and you're trying to guess what's in that soup, right? They like,
Yes.
Is there basil in that soup? Is there little bits of pasta in there? I'm not sure. And, we've trained our system on thousands of different recipes of soup, taken pictures of them, and then also taught them what the ingredients of those various soups were. And so now when you see a new soup, you take a crack at what's probably in that soup. Got it.
Yeah. That's
Okay.
that's and so for BARBIE in particular, we use this thing called the log Bayes factor. And so we're running these tests, so these retrievals with and without the molecule in it, and comparing them to see what results in a better fit. And then that gives us basically the likelihood of the presence of the molecule in the atmosphere, which we based off of. So we have 3 different kind of detection strengths from Benecke and Seeger et al. And then from there, we're able to really compare at what SNR, molecular abundance, and wavelength, we can strongly detect these molecules. And so that's kind of where the methodology behind like the paper and BARBIE. And so, from there we can kind of like analyze these detections and relationships.
Right. So in other words, you kind of know how strong the signals can be based on the telescope at different levels, and then you're going to run these through the sort of simulation of the coronagraph, and to understand or I guess the coronagraph simulations are giving you the different strengths, and then the software is saying, okay, if it's really strong, then it's easy. If it's not so strong, then maybe it's kind of hard, and if it's not very strong at all, then it's really difficult for you to be able to do it with the existing pipeline that's being proposed for each WO. Am I still?
Yeah, so we're kind of
Okay.
seeing like at what detection strength these different molecules will be at, using like the future Habitable Worlds Observatory at
Yep.
giving different parameters and stuff. Yeah.
Okay. And so I'm interested, I haven't read that paper, but I'm interested to sort of like, what are the scenarios? Like, is it the size of the primary mirror? Is it just the how well the coronagraph is going to work? What sort of defines those parameters for how good the quality of the data are?
Yeah, so for this particular study, we use the Planetary Spectrum Generator, which is a really great tool. It's open to use for the public. It is a radiative transfer tool that allows you to generate synthetic spectra of like basically any object you can think of. It's really amazing, and so it actually has a predefined LUVOIR template, right? So we were using that.
Right. The former name for
Yes.
the former LUVOIR was the former name for HWO. Yeah.
Yes. Yeah. And so it's not that we were changing, the diameter, or the aperture or anything. It was more we were changing, the signal to noise ratio is one, but more, given this range of wavelengths, which is what we were, interested in, defining that long wavelength cutoff, of course. So given this wavelength and then different molecular abundances of carbon dioxide, water, and methane, how would that impact our detectability of these molecules? And so we looked at carbon dioxide values throughout Earth's history because, when we're looking at a planet, we don't know what phase of, evolution it's going to be in. So it's important to really, get a wide variety of molecular abundances so we can see, like, if we were to look at this Earth-like planet in the Archean Earth kind of like phase, how would we be able to detect their carbon dioxide, for example, given like a modern level of water and methane? So that was kind of more the level of varying parameters that we were looking at. And so, we chose varying parameters and even a Venus-like CO2 abundance because we wanted to see, like, if you really cranked up CO2, would we be able to see it? Which, for anyone who doesn't know, Venus has like 96% of its atmosphere is carbon dioxide. So, like, that's a huge amount. So, like, hopefully we'll be able to see that, right? So just like testing it and figuring out the optimal bandpass or like wavelength where we can strongly detect these molecules.
So what did you find?
Yeah, so we first started with modern levels of water and methane and varied the CO2 abundances, like I was saying before. And we found that only the three highest CO2 abundances resulted in these strong detections. And so that's Proterozoic, Archean, and then Venus-like. And so Proterozoic is 1 to negative 2 volume mixing ratio, which if you're more familiar with like parts per million, you just multiply a VMR by a million.
Well, what are we right now? We're like, whatever, 400-ish or 450. I don't even know how many parts per. Anyway, we're in the 400-ish plus. Yeah.
And so then Archean is 1 to negative 1 VMR, and then a Venus is 9.6 to negative 1 VMR. And so with these modern levels of water and methane, we're only seeing strong detections for these three highest CO2 abundances. And we noticed that there are many different kind of plots in the paper, but we called them detectability plots, where they plot the strength of detectability at different signal to noise ratios across the wavelength range that we give. And we found that there was this kind of weird dip, right, in detectability. Like it was really strong, and then at some point it goes whoop, and then it comes back up. And so that kind of led us to be like, what is happening there? And this kind of gets back into that disentangling of spectral features. So when we look back at like a modern Earth spectrum, for example, we're seeing that there's like a huge water feature there, right? So this increase in water abundance is negatively impacting the CO2 detectability. And so from there, we wanted to see how varying levels of both methane and water were impacting CO2 detectability. And so we ran these tests, we ran the retrievals, and found that both increased levels of water and methane both negatively impact CO2 detectability across the board. And in fact, later we see that methane actually negatively impacts the detectability more than water does. Um, and so that was kind of the kind of main findings from how these three molecules interact with each other. And then overall, coming back to this like long wavelength cutoff for habitable worlds, we found that a bandpass center of 1.52 microns was the optimal little wavelength range where we could strongly detect CO2 in addition to water and methane at like reasonable SNRs.
So just like, again, I apologize. I need to,
No.
need to catch up here with you. So what you're proposing then is that of all of the different kinds of chemicals that you were trying to analyze, once you got to that 1.52 microns, that was sort of the sweet spot to give you the best detectability. And so really from a sort of biosignature perspective, if you want to see that interplay between methane and water and carbon dioxide in the atmosphere of a world, the telescope needs to be able to deliver to the astronomers that 1.52 microns, which, is that well within the current plan for HWO, or is that kind of ambitious?
Yeah, so actually, the bandpass center of 1.52 microns would actually extend all the way out to 1.68 microns. So that would kind of be the cutoff. And as far as I know, that is like reasonable. I know there are other studies that kind of come to that same conclusion of this like kind of around 1.7 microns for the long wavelength cutoff, where we would be able to get all of the spectral information of these different and various biosignatures that we're hoping for. And the great thing about that, as I was talking earlier, that's, before that 1.7 cutoff of where we would have to start cooling the telescope. And so, it kind of, works out that we're seeing these, strong detections of all these different molecules and biosignatures without having to go past this, cutoff where you'd have to start cooling the telescope and, go through all of those engineering complications as well.
Right. Oh, that's really interesting. That's good. That's good news then.
Yeah.
I mean, one of the things that I've been sort of seeing in my reporting over the years is that, I think if you listen to astronomers, say 20 years ago, they're going to say like, all we need to do is see the presence of ozone in the atmosphere of a world, or large amounts of free oxygen, or whatever. And then someone goes, well, actually rocks can do that. And they're like, oh yeah, okay, maybe it's not ozone. Okay, maybe we just need to see whatever, carbon monoxide. No, rocks can do that too. Okay, great. So turns out every possible molecule that you might hope to see in the atmosphere of an exoplanet, there are abiotic methods that can do the same thing. And that now the shifting has really come to, instead of it being, let's just look for that one smoking gun biosignature, that it's us better understanding the interplay of these molecules over the course of various seasonal changes. As the trees, as whatever the alien trees are bringing in, their oxygen, and then putting out exhaling their carbon dioxide. That's the kinds of changes that we're going to see to be able to build up that bigger picture. So you've been focusing on the water, the methane, the carbon dioxide. Is there like another kind of chemical regime that you think would be interesting to try and bring in as well?
Yeah, for sure. And so I recently started grad school, and so this work was done as a postbac at NASA Goddard, and so I've as I've been wrapping up this work, I have been, introduced to the world of these novel biosignatures. So in particular, my advisor, Dr. Edward Schwederman, he's very interested in methyl halides, for example. And so these are really cool. This is CH3Cl, CH3Br, CH3I. And these are really cool because they're produced both in marine and terrestrial environments by like fungi, microbes, fungi, plants. And so they're really cool because, we could see them both in these terrestrial planets, but also perhaps like Haitian worlds, so like hydrogen-rich ocean worlds, which, is a whole other thing. And also going back to like that abiotic, problem, right? Like, are these actually coming from, life? Is it actually being produced by life or not? Methyl halides, their abiotic production is much less than like the biogenic fluxes we see on Earth. So like if we were to detect them, theoretically our confidence should be higher because they should be more specific to life and like biotic production. And so moving forward, like I am very interested in kind of incorporating these methyl halides into the retrievals similar to BARBIE, and seeing how these molecules play a role in biosignatures and their spectra. But the current issue is that we have this knowledge gap where we don't have these cross sections, which basically tell us how the spectra should look and the spectral features that methyl halides have in the near infrared. And so that's kind of what I'm working on right now, is to obtain these high resolution absorption cross sections of methyl halides so that we can put them into these retrieval models and figure out, similarly, like depending on the abundance of them, would we be able to detect them? And I'm really interested in, given this 1.68 micron cutoff that I've defined in BARBIE, looking at carbon dioxide, methane, and water, would this cutoff be sufficient as well for molecules like methyl halides? And so,
And I mean, like when you're trying to observe these today, I don't know if you just like try to observe it in our own atmosphere or look in seawater. I'm not even sure how you would do this. Do you
yeah.
know sort of what wavelengths you would want to be using to examine them?
Yeah, so I for our work we'll be looking in the near infrared. So about like 0.7 to 2 microns will be kind of where our sweet spot is for looking and analyzing methyl halides. Um, and so that will be great for the Habitable Worlds Observatory, right? Because, we're going to be kind of in that range. Um, I'm I'm not sure how we look at it kind of today. I'm still learning about, all things methyl halides. It's only my second quarter. So, but yeah, for the project I, will be working on, it will be like in the near infrared region.
But it's interesting to me that you sort of have this, like the big molecules. I don't mean like physically big, but just sort of like the ones that compose most of the atmosphere. The things like
Right.
seeing water vapor, oxygen, ozone, carbon dioxide, methane. Like these are very abundant in various atmospheres. That those could give off a signal that is strong enough, but it doesn't give you that unambiguous detection of life. But it sounds like
Yeah.
some of those other chemicals that you're looking at, if you see them, are there methods, can rocks make them in the way that rocks can make other chemicals?
Yeah, so I know that they do have some abiotic productions. However, it's not near as much as, those other molecules like water and methane and, stuff like that. And so that's what kind of makes them interesting, stand out. Um, and so, like you're kind of alluding to, it's really important to know the context of the environment, right? Because so many things could be playing into, what releases certain molecules. And so that's something that we need to study further, and really get a grasp on. And I know many people are, already looking at this and looking at papers and, doing lab studies and everything. I know I wanted to actually bring up, I know there is a kind of a consensus of like, if we were to detect a potential biosignature, how can we actually be sure? Or like, how can we say confidently, this is a biosignature? And, it really requires a lot of analysis, right? And like, are we confident in the detection? Like, that's, one thing. Like, do we have enough information? Was the signal good enough? And then another thing is like going through all of the different production mechanisms. Could this be produced abiotically? How likely is it to be produced by just biotic, life, for example? And then, you have all of these different things that play into how we could be confident in a detection.
I mean, you just gave what I think is a dramatic understatement here. You're like, well, it's going to be a little tricky and people will not be entirely sure. Like, we have
Yeah.
seen the argument over the potential discovery of life with the Viking experiments, with the sort of the sample release on Mars. There is already a controversy about the detection of phosphine in the atmosphere of Venus. And again, Venus is
Right.
in our solar system. It is right over there. And yet astronomers will argue about whether or not there was phosphine detected and if that is an indicator of life. So imagine trying to make a conclusive case for this very subtle detection in a planet that is parsecs away from us. Like, that's tricky.
Right. Yeah. And I mean, part of me is like, will we ever really be able to like 100% be like, this
Yeah.
is life, right? Because really without going there, uh, like how can we 100% be certain unless, somehow they send us a message, it's some like intelligent life perhaps, but we're really probably going to be looking for like, this, some microbes, like, microorganisms. And so, yeah, like, will we, if we find these biosignatures and it alludes to this possibility of life, like, how certain can we actually be that there's life there? So that's another whole different question.
I mean, it's funny, with leading up to the launch of Webb, there was sort of this stuff in the media where people were really giving people the impression that Webb would completely rewrite our understanding of the cosmos, that it would overturn theories of the Big Bang, that it would, and the actual astronomers you could see were like, oh no, it's going to just, it's a better telescope. It's going to give us more information. It's going to help us fill in the missing pieces. And it feels to me that as we're all very excited about the Habitable Worlds Observatory moving forward, and we're excited about the potential for finally having a telescope that is going to be directly imaging the atmosphere of some other planet, I feel like I need to prepare my audience and the public in general, like, whoa, settle, you're not going to go, yep, there's aliens there, because it's just we're going to live in this world of ambiguity for decades, centuries, right? Until
Yeah. Yeah, I mean, I feel like I've heard a lot of, scientists be like, we're probably not going to be, conclusive on if there's life, in our lifetime, and it's it's kind of daunting, but it's also like, there's so much more to explore and like there's so much more to learn. And I think that's why so many people are so excited about, the potential of Habitable Worlds Observatory and, the potential of life because really, at our core, humans are just curious and we want to learn. And, we are on this, floating rock in the middle of space. Like, it's just, life is very precious. And the fact that we haven't, detected it yet and, possibly can, it just provides an insight for, how amazing, this, is.
Yeah, it is this unimaginably complex challenge that's going to require the sort of greatest minds of humanity and the most advanced tools pushed to their very limits to even take a crack at the very edge of this problem. And yet, for the first time in human history, we can. So let's. Yeah, so it's going to be more complicated than we thought. It's going to take longer than we anticipated. The result the answer to this philosophical, or this question, right? Are we alone in the universe? That we now, for the first time in the history of humanity, have a way to try and begin cracking this problem, and that we will, if we don't know the answer, we will at least start down this journey, and we will find out, did it take us decades, did it take us centuries to find out the real answer? Celeste, what are you obsessed with right now?
Oh, I, you know, overall, I'm just like obsessed with how we can, use our knowledge and all of these technical capabilities to, understand what is out there in the universe. And, especially I'm taking actually like an ecosystems through space and time course right now. And, using our knowledge of previous eras of Earth has been really interesting, and how we can use like, the five mass extinctions to, kind of learn about the present, for example. Um, and just how life is so resilient, but at the same time, like it could be gone, in an asteroid hit, right? So I think
Well, yeah,
just yeah.
I mean that is kind of interesting to me that you're mentioning that you looked at different kinds of eras, that while, say, the modern era of life might actually be really tricky to detect, these previous eras, the protozoic,
Protozoic, yeah, Archean,
the Archean, or the Venus, the runaway greenhouse effect, that there are other times in Earth's history that might be a much stronger signal, and that as we look out and see more and more of these planets, we might not get a strong signal for the kind of world that we would love to imagine, with alien trees, with the alien dinosaurs roaming around. But even just saying, well, it's fairly unambiguous that we're seeing a world like the Earth 1 billion years after our formation, or 2 billion years after our formation, that at least that gives us a crack. I find that, acceptable.
yeah,
Not
and
ideal, but yeah.
yeah, and I think like something else, like just the amount of possibilities about like how a planet could form and evolve. Like, our solar system has, great foundation, but of course there are a bunch of different planet demographics, right? Like that are different, like these sub Neptunes and super Earths and like everything. So I think that's also something that like I'm excited to, learn more about, and like how those come about and form and evolve and everything. How we can maybe compare it to Earth, and like, through the time, right? Through these eras. But yeah.
Yeah, it's interesting. And I wonder what the future might look like. Like, I wonder what a world that is several, I don't know, like a 500 million years, 1 billion years farther into our future. Because I know, like, for example, the sun is heating up, and it will have different effects on planet Earth. I wonder what future versions of Earth, is that more detectable, or is that worse?
Yeah, and like even the, our human impact, right? Like, imagine an Earth that didn't have humans on it, or like what would that look like, and how would they evolve differently? Like that's something else I think is interesting. In 500 million years, will we even be here?
Yeah.
Probably not.
Right.
Is my guess, but
Yeah. But the octopuses will have taken over. They'll be fine.
yes, they'll be good.
Yeah, exactly. Well,
yeah.
it's fascinating work, and these are the various bits and pieces that all really need to come together to bring this mission and make it happen. And any day now, merely 15 to 20 years from now, we will get that first data. Celeste, thank you so much for your time. Good luck with your research.
Yes, thank you so much for having me. It was great to talk about all things habitable worlds and astrobiology.
Awesome. I hope you enjoyed that conversation with Celeste Hagee. I'm going to sort of give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailout, Cooper and Ellie, Dark Finga, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Buck, Rankaidu, Richard Williams, Sean Sargent, Stephen Fallon Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. I hope you enjoyed that conversation with Celeste Hagee. Hopefully you have already watched the interview that I just did with Lee Feinberg, who is the architect for the Habitable Worlds Observatory. And, he talks about like, how do we give the astronomers the most pristine view possible that we can? But that is one piece of the puzzle. The next question is, if the astronomers get that pristine view, is the wavelengths that it's being designed for going to allow them to make those detections of the biosignatures? And that is the conversation that I just had with Celeste. The last piece of this trilogy is going to be, will the coronagraph be able to deliver the results? And this is possibly the trickiest technical problem of this entire telescope. You've got to get that 10 billion to 1 light sensitivity to be able to reveal a planet and block the light from the star. And this is no easy feat. And so I have completed that portion of this trilogy as well. I've done a ton of interviews about next generation coronagraphs, but I think the one that you'll find most useful is this interview that I did with Vanessa Bailey, who is working on the coronagraph for the Roman telescope. And that is the telescope that's going to be launching like next year. And it will be able to find these exo-Jupiters where you only need that 100 million to 1 difference in sensitivity, not that full 10 billion. But a lot of the same technology that went into the Roman one is going to go into the same, but more advanced into the one that's going to go with the Habitable Worlds Observatory. So hopefully that'll give you even more food for thought. I'm going to put links to the Lee Feinberg interview about the architecture of HWO, as well as the interview to the Roman coronagraph. And then with these 3 pieces together, you have a good sense of the technical challenges and what must be accomplished to reach this first image of an Earth-sized world orbiting around a sun-like star. All right, we'll see you next time.